Hey everyone, this is Pwn Encryptinator. It was a challenge as part of Texas A&M's CTF. Overall, very fun challenge. I think it teaches good fundamentals, and at first it looked impossible, but once you figure out what you're actually supposed to do, the solution was actually very simple, which I love those types of challenges. It says, I have made the super secure encryption engine. I'll encrypt any message and no one will ever be able to read it, not even me. And we're given a download file. The download file contains two things. First off, it contains the binary, and second, it contains source code, which is always appreciated. Again, I'm not going to cover most of it. Actually, let's run the challenge first. So we'll do encryptinator, a bunch of stuff. It's really not too exciting. The first thing is we can encrypt a message. So I'll say 1, and then I'll say hi, and that's it. And then we can say, I want to view the message. I'll give it an index of 0, and we get out our ciphertext. That's the whole binary. So going back to the source code, I'm going to go and only cover the exciting things. And like I said, there's two things. We can encrypt a message and view a message. So when we encrypt a message, there's two exciting things about the encryption function. The first thing is that it's doing an XOR encryption, and it's for the key, it's reading from dev random. So obviously not breakable by CTF standards or pretty much any standard. So it's just going to be doing an XOR, and since that key is not saved anywhere else, this seems pretty impossible to break. Like, you're not going to break an XOR encryption. You can't. The other interesting thing is the function that calls this encryption function is this randomize function, and this randomize function is recursive. Kind of strange. So randomize will call itself over and over depending on the iteration count, and we as the attacker get to control this iteration count. So we can have it recursively call itself a bunch of times, which doesn't seem too useful at first, but it ends up being very useful, as we'll find out. Yeah, and then if we keep going down, like I said, there's the two options. This is the first one, basically enter a message to encrypt. It's going to read it. Fgets always terminates with a null byte, so the string length does look a little bit suspicious. Maybe we could try to, I think we had a write-up maybe last week where we abused this with a malloc call, and we were able to extend a buffer past where it should go. But we're not going to be doing string length, or we're not going to be abusing that since fgets always ends in a null byte. So yeah, it's going to read in our message, it's going to append the flag, then it's going to encrypt it, it's going to generate a C with some random values, then it's going to, encrypt it, and that's it. And so once we're done, both the seed and the key are, lost, and it was encrypted with, XOR encryption with dev random, so it seems pretty impossible to break. This is how we view the ciphertext. It's going to ask us for a index, and then it's going to make sure that the index is doesn't go past the bounds of the ciphertext on the far side, and then it's going to give us the encrypted string that also contains our flag using the print hex function. And there's nothing too exciting about the print hex function. If you want to see if you can find the bug, it is in here. You'd have to pause the video because I'm about to say what the bug is, and the bug is right here. So scanf is reading a signed integer. I guess the bug is actually split across multiple lines. So since it's reading a signed integer, it's possible that index could be a negative value. And we can see they don't do an error check for negative values here. And so this is the bug that the challenge author placed. Since we're able to specify a negative value, this print hex will read down the stack. And if we remember how the stack is aligned, as we call new functions, the stack grows down. So it grows, in negative numbers. And so it is possible that we could see variables of other functions that were previously called using this little gadget. And so that's pretty much what our exploit is going to be. Like I said, there's no way to break this ciphertext or encryption algorithm, but if we can figure out what that original key that was being used and what seed was being used in that encryption algorithm, obviously we can just reverse, or we can do the decryption, and we should get back the flag. So pretty fun. One thing we had to be a little bit careful about, every one of these functions, like scanf and printf especially, they call 5 functions deep. So scanf will call some internal parsing function, and then some standard library functions. It'll go 5 functions deep. So it's going to clobber a lot of the stack. And so it's possible that this encryption function just isn't deep enough, I guess, that it'll be clobbered by all of this stuff. And that's why this randomize function, having it be recursive, was so useful. So we can specify the number of iterations, and so what we're going to do as part of the exploit is we're just going to push that randomize function down the stack quite a bit, and so that way it doesn't get clobbered. Because technically once the stack moves back up, anyone's allowed to use the stack below. as just like general best practices. Like that's free territory. So other functions are going to clobber it, but as long as we push it down far enough, nothing should clobber it, and we will be able to read off both the key and the IV, and we know what the ciphertext will be, and so then we can just XOR them all together and we'll get back the flag. So really not too hard of a challenge once you know what to do. Maybe the only, like, I wouldn't say difficult, but the technically challenging thing is we need to figure out what those offsets are. So like I said, we can specify a negative number, and that negative number will read relative to the ciphertext buffer. And so we need to figure out how far away the key and the IV are from that buffer. Thankfully, it's pretty easy to do. We can do this in GDB. So I set a breakpoint. Oh, this is the solve script, by the way. Standard pwn tools, disable warnings, set some context, launch the process. There's nothing too special about this one. I put 2 breakpoints. One is at randomize 99 and one is at encrypt 157. And by inspecting GDB at these 2 spots, we should be able to get the stack location of both the key and the IV. And these specific points, one of the breakpoints is right here. So when we break here, we can see what arguments are being passed to encrypt, specifically the seed, and we'll be able to see the seed's location on the stack. So that's one of them. And the other place I break is right here. When we're doing an fread, we'll just see what the arguments are to fread, and we'll be able to get out the address to the key. You could do it anywhere. I just found that these locations were pretty simple to break on and leak these values. And to see what that looks like, let's go here. We'll cancel this. Let's do python 3 solve.py. I'm sorry it's a little bit small, but we need to be able to see the registers. I can make it a little bit bigger, I think. Bigger. We need RDX. Okay, yeah, that's good enough. So let's then do a continue. We can't see RDX now. There we go, we can see RDX. Sweet. So we are in randomize, about to call encrypt. For some reason, pwn tools or pwn debug has this wrong. I think it thinks it's a different encrypt function. I'm not too sure, but thankfully the calling conventions or the ABI is standard for this. And so we know that this argument specifically will be in register RDX. And so this is our IV. So encrypt, if we go back to the source code, we can see encrypt is called with message length IV. And we want IV, so that'll be RDX. And so that means this is the IV on the stack. So what we can do is take that and put that in our solve script. I already have one here. I'll just comment this out. We'll copy over new values. So this is the location of where our IV is. We also need the location of our ciphertext. It's the same one for both the plaintext and ciphertext. It uses the same buffer. So anywhere we see this, the plaintext, which is right here, we can just copy that address out. It's all over the place. So we'll copy that. That'll be our buffer. And last, we need the key. So we're going to continue. And now it braked on the encrypt fread call. So this is about to read the key from the dev random file. And as part of that, it has to pass in the buffer. And so we know the buffer that's being passed in is our key. So we'll copy this stack address out. We'll say that's the key. And that should be everything we need. Like I said, really, we don't really care what the specific values are. We just need to know the offsets between them. Like we need to know the difference between the IV in the buffer and the key in the buffer, so that when we ask for the ciphertext index, we know which negative number to pass. Now that we have them, the rest of the script is pretty standard. We're going to call encrypt. Like I said, as part of the encryption function, it's a little bit strange, but the very first byte is the number of iterations. Just technical detail. So I specify this many iterations. If I did more than that, I think I actually got a Stack Overflow. So I found 40 hex was a good number. Then after that, we're going to ask the program for 3 different subsections of ciphertext, I guess. The first one, we're going to leak the IV. So we're going to pass it, negative. I think I actually have it somewhere in here. Yeah, the IV is stored at -3064. So it's 3 kilobytes back on the stack. Then we're going to ask for the key, and that is 3200 bytes back. And then we're going to ask for the ciphertext, which is at index 0. And we take those and we XOR them all together, and we should just get flags. So let me rerun it without GDB, and we'll see if we actually get the flag with our newly calculated values. We'll run everything, and then here's the XOR, and bam, there is the local flag. So it worked, our little XOR. We can try running it on remote. Let's copy this out. Let's close. We'll run it remote. It's a little bit slower, but there we go. Gigim, oops, bad error checking. And this is just referencing the fact that they didn't check to see if the index was less than 0. But yeah, that was the solution. Overall, very fun challenge. It's a real security issue, not doing these index checks. And, it was a fun challenge. It seemed impossible at first, but once we knew what we were doing, it really wasn't too bad. Yeah, that's it. I'll see you at the next CTF. Cheers.